Hey guys, welcome back. Last time we took a look at resting membrane potential. This time we want to look at polarization a little bit deeper. Now recall, polarization is the concept that says that at rest the cell membrane is at a polarized state. It's net positive on the outside in respect to the inside of the cell. Now that is going to give us a membrane potential at rest. Now, things that would change that membrane potential would be anything that would alter the permeability of the ions and or anything that would change the concentration of the ions on either side of the membrane at rest. Now, when we're looking at polarization, some terminology that I want to just slowly go through here. There's two types of signals that produce changes in the membrane potential, and those signals are going to be known as graded and action potentials. Now, before we look at the types of potentials, let's look at a few key terms that we're going to have to depend on knowing as we work our way through these graded and action potential. And let's use this diagram here that shows the electrical events that's occurring during an action potential to break down the components that we can measure. First, we can measure resting state. Now, resting state, as you can see from this image, is going to be at about a negative 70 millivolt charge. Now, resting state, by definition, is going to be when the sodium and potassium gates are closed. No ions are moving across those gates, but we do still have that diffusion of potassium and sodium and chlorine moving across at rest based on their permeability capabilities. Now notice at some point we do have a change in the membrane potential. Now that change in the membrane potential, if we want to think of it as resting membrane potential being impeded by some type of electrical chemical signal, and we see a reduction in the membrane potential. And that reduction we call depolarization. And depolarization is when we see this curve go from a negative 70 towards 0 millivolt charge. We're taking a polarized charged battery and we're depolarizing it. And the way we do it in reality is by opening up sodium gates. So the electrical vent will come down and trigger open sodium gates. And we'll see the movement of sodium into the cell from a region of high concentration to a region of lower concentration, bringing with it its positive charge. Now again, if you bring a positive charged ion into an environment that is basically negatively charged, it's going to cause the inside of that environment to become less negative. And that's what we see happening here as the charge approaches 0. In an ideal world, the sodium gates would close completely at a 0 millivolt when we totally, however, the 0 millivolt is actually going to be when the sodium gates are triggered to close, to begin to close, and they take a little while to close. So you see that they approach that positive 30 millivolt charge before they're completely closed and start to go downhill. That difference between 0 millivolt and positive 30 millivolt charge is something known as overshooting. Now, number 3 you see listed here is repolarization. Now, repolarization is going to begin as we approach the 0 millivolt charge, because that 0 millivolt charge is going to, one, trigger sodium gates to start to close, but it's also going to trigger open potassium gates. Now, as these potassium gates open, potassium is going to move from the inside of the cell out into the extracellular space, carrying with it its positive charge, removing the positive charge from the inside of the cell. Now, that influence is going to be realized as soon as the sodium gates are completely closed. Potassium is moving out. Potassium takes with it its positive charge, allowing the inside of the cell to become negative again, to approach the negative state. Now, notice that as it approaches that negative state and it gets back down to that resting state of a negative 70 millivolt, that negative 70 millivolt charge is what's going to trigger the potassium gates to start to close. They're a little bit quicker to close, but notice they still do allow more potassium to move out and allow the charge to actually approach below the resting state. That event is known as hyperpolarization, or is also known as undershooting. Now, the gates will close though, and as the gates close, the potassium gates close, the sodium gates are already closed. Then we can use the ATP-driven sodium-potassium pump to reestablish and bring us back to that resting state one more time. There's one other key term that's listed here that I want to make sure that we address. That's threshold. Threshold is going to be a crucial level of depolarization in which the localized depolarization causes a cascading of positive effect to occur that will result in the spread of this electrical event from a local depolarization to a depolarization event that occurs along the entire length of that axon. We'll call that propagation. And we know that phenomenon is all or none phenomenon because the localized depolarization will have to occur in a given amount of time and a given amount of depolarization for that localized event to result in the event to occur the entire length. But if we do reach threshold, the strength of that electrical event will be the same from the point which it begins to the point which it ends, which is usually at that neuromuscular junction. Next time around, we'll take a look at the electrical events associated with an action potential and a gradient potential. You guys have a great day. See you soon. Please be safe.